Well, good morning, Elch 2 Extended. Mr. Kruger here today. Today we're going to be looking at lesson 1.8. There's one more lesson, 1.9 tomorrow. Then we're going to be reviewing, and we'll be having a summative assessment on Thursday or Friday, if not both days. Next slide here. Let me get rid of that. Your to-do list is to finish up this video. Make sure you know what's going on in the notes, and then complete your 1.8 try on your own assignment. And what we're looking at today is, if we kick back into Algebra 1, you explored a lot of different functions, two of which were both linear functions and exponential functions, and how those functions were modeled via their graphs, tables, and or equations. So as a little warm-up thing we're going to do here is I'd like you to actually hit pause in a second and then classify each of the four tables as linear, exponential, or neither, the same for the equations, and then the same for the graphs. And then unpause after you get that done, and we will go over that, okay? So as I look at number one, the table, when I look at the number of seats, I always think about an X and a Y when I'm talking about a table of values. And when I'm looking at my Y values, I go from 20 to 25 to 30, and I can totally see that I'm adding 5 units each time. And whenever I use repeated addition, as my X's go up term to term, basically if I keep adding 5, that's repeated addition. Repeated addition is a linear function. And when I look at a linear function today, we're actually going to be talking about sequences. When I see a linear sequence, as this data models, it has what's called a common difference, D, and that common difference is the number that you are adding each time, okay? When I look at data number 2, I got an X and I got a Y. Well, if I go 2 to 6, 6 to 18, well, I'm obviously not adding the same number like I was before, but if I take 2 times 3 and I take 6 times 3 gives me 18, and I take 18 times 3 gives me 54. 54 times 3, that gives me 162. Well, if you think about it, back in the day, repeated multiplication is an exponential function, and exponential functions have what's called a common ratio, and the common ratio, R, is what you are multiplying by each time. In this case, it would be 3. Well, when I look at my data here, my days and my values, I go 1,000 to 900. That would be adding negative 100, but when I go 900 to 810, well, that's not adding negative 100, so it couldn't be linear. I'm not adding the same thing each time, but if I look close at it, I'm taking it times 0.9. 1,000 times 0.9 is 900. 900 times 0.9 is 810. 810 times 0.9 is 729, and so forth. Okay, so repeated multiplication again gives me an exponential model there in a table, and my R value that I keep repeating by is 0.9. And now a lot of people think, well, couldn't I just be dividing by 10 each time, or dividing by 9 each time? The answer to that is no, because we're not. Or I could put it in a fraction. I could be multiplying by 9/10. Okay. This last one down here, 10,000 to 8,000, 8,000 to 6,000. Ooh, that's adding negative 2,000. And that's adding another negative 2,000. And I'm not going to say I'm subtracting 2,000 really, because I'm adding negative 2,000, because when I have a common difference, it is through repeated addition, okay? Everybody's going to try to really split hairs with that, but I'm actually adding negative 2,000 each time for a linear function, and my common difference would be negative 2,000, okay? Now that's just buzzing along there. When I look at an equation, just looking at this equation, equations are much easier to identify. This could not be linear, because linear always looks like y equals mx plus b. This is exponential, And the reason it's exponential is because my exponent is a variable. And when I look for the common ratio in an equation, it's whatever my repeated multiplication I'm constantly repeating as that exponent goes 1 to 2 to 3, I'm multiplying by my r value of 3/4 over and over and over. Okay, the next one, p of x equals 3 plus 5x. Well, that's linear. Okay, don't worry about the form in which it's, or the order in which it's written in. It's that way. Well, what do I add each time? My common difference, I'm going to be adding 5 more each time I go, because as I plug in a 1, I'm adding 5. As I plug in a 2 for my second term, I'd actually be adding 10, which is 5 twice. Okay, here again, linear with a common difference of, in this case, we really want to see r of x equaling -15 plus -3 times x. So my common difference is -3, and that sign just gets pulled along with it in a common difference. Here again, exponential because there's a variable in there. So my r, I'm going to be repeatedly multiplying by the number 6. Okay. When I'm looking at graphs, graphs aren't too bad. If the graphs look like they're going to make a straight line, like this one does, it's linear. Okay, linear means line. Don't forget that. Linear is line. These do not make a line. This makes a curve that starts to grow. This would be an exponential. And when you did exponential, we had both growth and decay. This one from left to right is growth because it's growing. We don't really need to divulge into that too much right now. And as I look at this one seems to be falling, and it's not a line, so it's exponential yet again, but this would be decay is how we call them, okay? So as we move past here, we're going to be looking at arithmetic sequences. A few new definitions. You did work with these in Algebra 1, I know. Excuse me. What is an arithmetic sequence? Well, it's a sequence of terms in which the difference between any two consecutive terms is a constant. Well, when I look at this, when I go 4 to 7, 7 to 10, 10 to 13, I'm saying, oh, plus 3, plus 3, plus 3. I'm adding something common between each term, plus 3. So to get to my next term, I obviously have to hit plus 3 to give me 19. And then I would have to say again, plus 3, that's going to give me 22. Plus the next one would be another plus 3, that's going to take me to 25. My common difference, my D, what's the common number I'm adding between my terms each time? Well, it is 3, okay? Are arithmetic sequences related to linear or exponential functions? Well, if I'm adding 3, I'm constantly adding, making it more of a constant rise or constant increase, so they're going to be linear, okay? And when we look at these linear arithmetic sequences, the common difference related in a linear function, well, let me just come back here and let's just look at one of these equations. This is a linear equation, and the common difference relates to the what? What would that be called? Yes, you're right, that would be called the slope, okay? So as we're cruising along through here, there's actually a couple types of arithmetic sequences, okay? You have a finite sequence, and what that is that's a sequence that will stop or end. Notice this thing ended. There's 1, 2, 3, 4, 5 terms in there, and it stopped, okay? When I'm looking here, is there anything in common going between this finite sequence? Well, 25 to 21. If I'm thinking about it, I added -4, didn't I? And then how about 21 to 17? I added another -4 again. -4. You can think of it as -4, but we're really adding -4. Okay, so this one's going to have a D because it's linear, and the value of that D is at -4. Okay? Well, let's look at 36 to 72 to 144 to 128. Well, 36 plus 36 is 72. If I added another 36 to that, that gives me 108, not 144. I'm not adding the same thing in this time, so I must be multiplying by something in this particular case. And when I see 36, I'm saying, what? Times 2, times 2, times 2. So this is going to have a common ratio because I'm multiplying this time, and that value would simply be 2, okay? We also have infinite sequences, okay? And these are terms that we're going to come back to later in the year. There's not only arithmetic sequences, which are like linear functions, there's also geometric sequences, which have common ratios and are exponential. Okay, so we will come back to these. Both of them have finite sequences, and all a sequence is a list of numbers with commas between them, okay? And there's infinite sequences, lists of numbers with commas between it, but notice the difference here. This is a comma, dot, 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 and that comma, dot, dot, dot means it's never going to stop. It's going to continue on. Meaning if you continued this pattern, okay, you will die before you finish the pattern because it goes on forever and ever and it never stops. Well, check it out between these numbers. What happens? Is this going to have a D or an R? Well, 50 to 55 to 60 to 65 to 70. Looks like it's going to have a D. Looks like we're adding 5 each time. Well, what happens when I go from 200 to 20, 20 to 2, 2 to a fifth? Yeah, that's really not showing me anything that I'm adding. Okay, I'm not adding, what would that be? Negative 180 and then negative 180. No, what am I actually doing here? Well, if I take 200, and everybody's going to say, oh, it's divide by 10. Well, yeah, when I do divide by 10, I come to 20. But when I do divide by 10, I do come to 2. When I take 2 and I divide it by 10, I do get a fifth. But it's a common ratio. And please understand, a common ratio is through multiplication. And if I'm dividing by 10, that's the same as taking 200 times 1/10. Okay? So I'm going to say 1/10, or if I called that 1/10 as a decimal, I could call it 0.1, okay? So what that does is that just shows me an infinite sequence, basically, that they happen both ways with a common difference or a common ratio. Mainly, we're going to be talking about common difference today. And if you're looking at these numbers and you're like, crumb, I can't figure out how to find it. Well, to find the common difference is you take a term, say 55, and you subtract the term just before it, so minus 50. What does that give me? That gives me 5. Ooh, my common difference. But that has to be consistent through the whole thing. You should be able to pick any terms, like say 65, and subtract the term just before it, say 60. You better get the exact same number because that's what's common between them. That's how you actually, if you don't see it, that's how you find the common difference, okay? And then from here in our sequences, we are going to be defining 2 different things here in a bit. You did do all these in ELCH 1, and you took a year off there with geometry, and you're going to hit them again in ELCH 2 now. But we have 2 types of formulas. We have what's called a recursive formula, which is a formula used to generate the next term in the sequence, okay? So describe in words how to find the next term in an arithmetic sequence. Well, what you're going to do is you're going to add the common difference to the term just before it. And if you do that, you'll get the next term, okay? Just like up here, I have, I'm just going to come here for an example. I'm going to get rid of that business. Whoa, get rid of that. If I have my first term, term 1, if I add the common difference of -4 to that, 25 plus -4 gives me the next term. 21 plus -4 gives me 17. 17 plus -3 gives me 13. And I just continually add the common difference. That's how you use a recursive formula, okay? They also have what's called an explicit formula. And an explicit formula is a formula used to generate any desired term in the sequence. So how would we use these? Well, when we have our explicit formula, you simply just plug in the term number. What do you mean by the term number? I'm going to explain here in a minute what I mean by the term number, and you'll see it. But doesn't that just kind of sounds like, whoa, spell right, Kruger here. Come on, back it up. Like, I don't like my K, so I'm making a new K. Sounds like we're using an equation. And that's exactly what an explicit formula is. It's an equation. We put a number in, it gives us the explicit number out. Recursive formula, we can't really just plug anything random in. We just have to have a term and add the next term to it. Well, let's get into the nuts and bolts of this little bugger here. Exploration of the formulas and common notation used in sequences, because like I said, sequences are just lists of numbers. Well, if we're looking at this one, 3, 9, 15, 21, 27, I don't know, I don't know, ... I don't know, okay? How are terms written in formulas? Well, we would say a sub 1 actually equals 3, and this little 1 down here, that means the A stands for arithmetic, term number 1 is 3. Arithmetic term number 2 would be 9. Arithmetic term number 3 would be 21, just as they are explaining right through here. Okay, and the ... between there just means it continues. So if I'm looking here, I can see plus 6. Plus 6. Well, what's 27 plus 6? 27 plus 6 is 33. 33 plus 6 gives me 39. Notice I just added a plus 6 because I went term 1, 2, 3, 4, 5, 6, 7. And then between here, now I want the 10th, means I have 8, 9 to get to 10. So how I would assume most people are going to find out what this 10th term is they're going to say, okay, I need to add 6 to this, and that's going to take me to, what, 45? And then I got to add, and that's that term, then I got to add 6 to that. That gives me, what, 51? And then I got to add 6 to that term to get me to the 10th term, gives me 57. What I did there is I used the recursive formula to find the 10th term, okay? And we just list them out. And that's just adding them through. Well, what other notation do you see in formulas? Well, lots of them. When I look at the actual formulas, I have what's called the common difference. That's how much it goes up or down by each term written as D. We have A sub n. A sub n is the nth term in a sequence. Nth term meaning I don't know how many terms are in here. If there's 10 terms in that sequence, the nth term would be the 10th term. And here's the confusing part. A sub n minus 1 is the term previous to the nth term. Well, that doesn't make sense, but it will, okay? So here's my recursive formula. Basically what this means is, okay, let's say I want to know what A sub 3 is, okay? Now I have just defined, right here, I've just defined n equals 3. In order to find this third term, I need to find A sub, look at that little subscript, that's going to n is 3 minus 1, and then I add D to that. So that means I find A sub 3 by taking A sub 3 minus 1 is 2 and adding D to it. So I find the third term by using the second term and adding the common difference. That's the recursive formula. The n minus 1 just stands for, in this case, if I want A sub 3, n minus 1 is the term just before it, so that would be A sub 2. The explicit formula is the one most people usually like to use more. I have A sub n. This is any term I'm looking for. A sub 1, that is the first term I'm looking for in the sequence. D is my common difference, and what n is always an integer. It's always an integer, meaning it's always 1, 2, 3, 4, 5, 6, 7, and it goes on and on. We will never put negative numbers into a sequence, into an explicit formula. We're never plugging negatives in here. We're never plugging decimals. We're never going to find what is the 1.5 term. No, there's a first term, a second term, a third term. So we only plug integers into sequences. Okay, well, let's check this out. You intuitively, or I intuitively, tried to show you using a recursive formula to find the 6th and 7th term. And what I did was I extended that out and I used it to find the 10th term, because I added the common difference to get the 8th term, I added the common difference to get the 9th term, then I added it again to get my 10th term, okay? But what if we don't want, what if we don't want to find all those terms in between? What if there's too many terms in between? What if I wanted to find a sub 2003? Okay, I don't want to have to start there at the 7th term. I don't want to have to add that on 2000 or an obnoxious amount of times, okay? In order to do that, we would use an explicit formula, okay? And how the explicit formula is run, okay, this is a general formula of how to write an explicit formula for an arithmetic sequence. And in order to do that, we need to know the first term and the common difference, or ways to find them. And I'm not going to extrapolate on that much, but basically, if I'm looking, here's my sequence we're talking about, okay? What is the first term in this sequence? Well, the first term is 3, okay? What is the common difference? Okay, D is the common difference, but what is it? What am I adding from term to term to term? You're right, it's 6, okay? N is the number of terms. How many terms are in this particular sequence right here? There's 1, 2, 3, 4, 5 terms in that sequence, okay? Now just to extrapolate out a little bit more, here's a little bit of a visual on it, okay? So in order to go 3 to 9, we added 6. From A1 to A2, we added 6. A2 to A3, we added 6. A3 to A4, and we kept going. And we added 6 to get to A4 to A5, okay? How many differences were used in this sequence just to find these 5 terms, okay? How many times did we physically add the common difference? 1, 2, 3, 4. We used 4 of them. How do we see that in the formula? Well, we see that in the n minus 1 that is in parentheses right here, right next to the D. That tells me how many times I have to use the common difference to get there. What do you mean, Mr. Kruger? Well, if we're looking for a sub 5, and I was in there, my A1 is 3. Here's my common difference of 6. I'm putting 5 in there. 5 minus 1, I used my common difference 4 times. So rather than starting at the first term to get to the 5th term, okay, all I'm doing is I'm taking the first one and I'm adding the common difference of 6 4 times to get to the 5th term, because to find that 5th term I had to use the common difference 4 times. So common difference times number of times used is 4 gives me 24. I add that to my first term and I get the 5th term, okay? Well, now let's find that to find a sub 10. Well, I'm really looking at a sub n equals my first term, and I'm going to rewrite this all out just like we wrote it, a1 plus d to the n minus 1. If you were writing your explicit formula, you have a sub n equals the first term in this sequence that they gave me above is 3, plus my common difference we found is plus 6. So I'm adding 6 n minus 1 times. Now, what is n? N is the term number we're looking for. So if I want to find a sub 10, a sub 10 is going to equal 3 plus 6 times 10 minus 1. So obviously, hopefully it's obvious, to find the 10th term, how many times did we have to use the common difference? 3 plus the common difference we had to use to get to the 10th term. We had to use it 9 times, okay? So that's 3 plus what the heck is 9 times 6. 9 times 6 is 54. So a sub 10, my 10th term, would be 57. Okay, that's how you would use it. Hopefully that makes sense. So what we're going to do is we're going to zip over here to this last page, or second to the last page, a couple examples. When you want to find the next term in your sequence, you can multiply or add the common difference arithmetically to the previous term, or multiply the previous term by the common ratio geometric. We're not doing anything geometric in here. This is the idea of the recursive formulas. When you want to find a much later term in the sequence, you need to know what? Well, it really makes sense to know what the explicit formula is. So what we're going to do here is we're going to have 3 sequences. We're going to have sequence number 1, sequence number 2, and sequence number 3. And we're going to find how to find all these bits and pieces of it. Okay, well, when I'm looking at this, I'm going to come across the top. They're telling me it's an arithmetic sequence. Why? Well, what do I add to 3 to get 11? I said plus 8. Well, if I add 8 to 11, do I get 19? If I add 8 to 19, do I get 27? Why, yes, I do. So I can see my D equals 8 here. Because it has a D, it's an arithmetic sequence. What is my recursive formula? Well, these are kind of crafty. My recursive formula always looks the same. I can find any old term, a sub n, by taking the term a sub n minus 1, the term just before it, and adding that common difference, okay? And I can find that, but in order to use recursive sequence or recursive formula, you have to have a starting point. So let's say they're going to give us a starting point. Our first term started at 3. Knowing that, I can find the 10th term by adding 3 9 times, or excuse me, by adding 8 9 times to 3. What is the explicit formula? Well, the explicit formula, I can find any old random term by taking the first term, which is 3, adding the common difference times n minus 1. That n minus 1 is in every explicit formula you will write, okay? And it is pretty important to notice, because to note that it is a sequence. N can only equal integers, 1, 2, 3, and so on. No negative numbers. I don't put 0 in for n, and we go from there, okay? Well, when I'm looking at this, okay, compare this recursive formula, boy, that sure looks like a recursive formula. That looks like I'm adding a common difference to it, doesn't it? And I have a starting point, a sub 1. Well, that means my first term is 20. And if I add 10 to 20, I get 30. And if I add 10 to 30, I get 40. And if I add 10 to 40, I get 50. And if I add more, it keeps going on and on. What did I do? I did plus 10, and I can see the plus 10 in my recursive formula, so it's arithmetic. Okay? What is the explicit formula for this one? Well, now that I know a whole bunch of terms, okay, I can say any old rogue term, a sub n, is found by taking that first one, 20, adding the common difference, n minus 1, times to it. But remember, n is 1, 2, 3, and so forth. They have to be integers, okay? Check it out. I can fill these things in any way I want to. It's kind of following the pattern here, but I can see this kind of models y equals, I'm going to say b plus mx, okay? Because this is going to be a number. It's like plugging a number in times that. So it's arithmetic. Okay, well, what is my regular sequence? Well, because I know here this is my first term, I know recursively a sub n, any term is found by taking the term just before it and adding the common difference. Well, I'm saying a sub 1 here is going to start out with 5, because I know that's my a sub 1, a sub n equals a sub 1 plus d times n minus 1. And this is following that pattern. So I just said a sub 1, 5. Then over here, a sub n equals a sub n minus 1 plus my common difference. Ooh, isn't that kind of crafty? I can see I need my d right here. And when I cross-reference my d here, I can see d is 20. And a sub 1 starts at 5. So I can come over here and I can say first term is 5. Next term is plus 20 is 25. Plus 20 gets me 45. Plus 20, 65. Plus 20, I'm not going to stop. I'm going to stop, or I could keep on going. Okay, so that's how you can identify. We should be able to give you, bottom line is what I'm saying, we should be able to give you an explicit formula. From that, you should be able to write for us the recursive formula, what kind of sequence it is, and write out the sequence. Or if we give you the recursive formula, you should be able to find the other three. That's the whole point of that page. The very last one, what I did for time saving here, because there's a couple word problems, there's lots of applications and sequence and series and things, but we're only looking at arithmetic sequences here. What I did was I took time and I just made a little chart here. There's lots of ways to do this, but I'm going to put this together the same way I just taught this lesson. And the sum of the interior angles in a triangle is 180 degrees, and a quadrilateral is 360 degrees, and a pentagon is 540 degrees. How many degrees are in a decagon? And they want us to use an explicit formula to find this answer. So I need to organize my brain, okay? I really need to organize this. So I can see right here, triangle is 180 degrees. So my first term is a triangle with three sides, 180 degrees. My second term, is a quadrilateral. So quadrilateral, quad is 4, has 360 degrees, okay? A pentagon has 5 sides. That's going to be my third term, has 540 degrees, okay? We are going to say dot, 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 dot. What do we want? We want a decagon. A decagon has 10 sides. Angle sum, I don't know. That's what I'm looking for. But what would the term number be? Well, check this out. Look between your term number and the number of sides. Well, if my first term has 3 sides, my second term has 4 sides, my third term has 5 sides, check it out. The number of sides is always 2 more than the term, which means the term number in this case would be 2 less than the number of sides, okay? So I have, these are my n's. These are my n's that get plugged in. Well, I can kind of look term to term, term to term. I can see D is 180, right? I can see the number of degrees because they want to know how many degrees. So my first term, degrees, my a sub 1 is 180. So all I know to write an explicit formula is a sub n equals the first term plus common difference times n minus 1. So if I wrote this out, any term, a sub n equals my first term I found out of my table, 180, plus my common difference out of my table, 180, times n minus 1. Well, the way I laid out my table is if I want to know how many degrees are in a decagon, decagon has 10 sides, that's going to correlate to my term number 8. So I'm looking for a sub 8, and I'm going to find that by taking 180 plus 180 times 8 minus 1. Okay? Well, if I type that into my calculator, I am going to get 1,440 degrees. Okay, I can type all that in. Notice if I want the 8th term, I'm using the difference 7 times. Okay, yes, there's a shorter, faster formula you used in geometry for that. It's modified from this, and it's modifying our n's in the terms to use that one, but no big deal. Okay, last one. Franco invested $20,000 into a business as a loan. The business guaranteed to pay Franco $1,500 each year that his money stays with the business. How much would the business need to pay Franco if he decided to end their relationship after 8 years? That kind of sounds to me like they are looking to find a sub 8, right? That's what it sounds like to me. Find a sub 8. Well, in order to find that, because this whole thing is on arithmetic sequences, linear sequences, in order to write my a sub n equals a sub 1 plus d times n minus 1, okay, what are we doing? What is a sub 1? A sub 1 is the first year. Well, Franco invested $20,000, so that's the money they're going to have to pay him back. That was the first term. If he pulled it before the end of the first year, he's going to get his $20,000 back, right? What is the D? What did they agree to pay him every year? $1,500. Okay, so I can say A sub n is $20,000 plus my 1,500 times n minus 1. This is a formula. I could find out if you left it in there. We can find out, and I know there's other ways to do it, but we're doing an arithmetic sequence. We're writing a function. We are not just finding a number. We're actually writing a function looking like thing, I'm going to call it. I shouldn't call it a function. We want to find a sub 8. So we're going to take the initial $20,000 plus 1,500 times that 8 just gets plugged in. And I know everybody's saying, well, Mr. Kruger, if I want to know 8 years, I know if I need the 8th year, I need to multiply the common difference 7 times. So can't I just take 7 times 1,500 and then add his initial investment? And I'm going to say, yes, you can, but please do it like this. So we can say a sub 8 equals 20,000 plus, well, what's 9 times 1,500? I think that's going to give me about 10,500. So in the end of the 8th year, if he invests his $20,000 and they just pay him $1,500 a year and he opts out at the end of the year, they owe him a check for $30,500. Okay? I hope you guys have a good rest of your day today. We may or may not see you on office hours. If not, have a great day.